So hello everyone, and welcome back to the second day of our Welsh lectures event. So we had the public lectures in the evening yesterday, where both speakers gave accessible talk to a wide audience. And today, both speakers, Professor Sachdev and Professor Koyar, will present colloquium level talks for a broad physics audience. So I would like to hand over to my colleague, Hye Young, to introduce Professor Sachdev.
Okay, thank you, Aaron. So it's my honor to introduce Professor Sachdev. We had a wonderful talk from both of lecturers yesterday, and he will continue another talk today, which is more colloquium style. So we had an introduction yesterday, but I just want to have a short, brief, bio. So Professor Sachdev is Herschel Smith Professor of Physics at Harvard University. He was educated at Indian Institute of Technology, MIT, and Harvard. And his honor include the Dirac medals and Onsager Prize. His research interest is basically a many particle quantum entanglement that we heard yesterday. I just want to read one of his prize citations that include basically a list of his works. Professor Sachdev has made a pioneering contribution to many areas of theoretical condensed matter physics. Of particular importance were the development of theory of quantum critical phenomena in insulators, superconductors, and metals, the theory of spin liquid, state of quantum antiferromagnet, and theory of fractionalized phases of matter, the study of novel deconfinement to phase transition, the theory of quantum matter without quasi-particles, and application of many of these ideas to a priori unrelated problems in black hole physics, including concrete model of non-Fermi liquid. So with that, he's going to tell us today another large and small, but different context, the Fermi surface, large and small. Okay, with that, Subir, floor is yours now.
Okay, I hope you can see my screen clearly. So thank you very much, Hye Young. It's a real, thank you for that very kind introduction, and thank you for the invitation to give these lectures. I enjoyed my presentation last night, and I hope I will also, my presentation today will similarly generate some discussion. Okay, so let me just mention at the outset towards some of the very recent work that may mention in passing towards the end was done with Yahui Zhang, who's a postdoc at Harvard, Maria Tikhanovskaya, and Alexander Nikolenko, who are students, graduate students at Harvard. Okay, so I showed this picture last time about ordinary metals, how they have free-flowing electrons which behave like quasi-particles. So today we want to study metals in a little more detail, but let me view one of the basic properties of an ordinary metal at a little more technical point. In addition to the existence of quasi-particles, really the most fundamental property of an ordinary metal is the existence of the Fermi surface. So if I take free electrons with momentum k, moving through the lattice with some dispersion epsilon of k, then for free electrons, you just occupy the lower energy states. So there's a Fermi energy, and all states below the Fermi energy are occupied, and all states above the Fermi energy are empty. And the boundary between these states is what we call the Fermi surface. So this Fermi surface is really the central actor in all of the properties of a metal at temperatures much below the Fermi energy. Typically, the Fermi energy is 10,000 Kelvin or even higher. So at room temperature and below, we need only worry about the electrons which are close to the Fermi surface. And that's why it's the most important thing to worry about in any theory of a metal. Now there's a remarkable, and also, sorry, before I get to the remarkable fact, we can constrain the size of the Fermi Fermi surface simply by counting argument. So the electrons are occupying the states inside the Fermi surface, and there's one state per momentum, where momentum is quantized somehow by the size of the crystal. So you can count up how many electrons you can put inside the Fermi surface. And that must equal the total number of electrons that are moving around in the crystal. And so you come up with this constraint that the volume inside the Fermi surface divided by a phase space factor is just the density of electrons per spin. Okay, now we've got to turn on interactions between the electrons. And that leads to probably one of the deepest theorems in the theory of metals, sometimes called the Luttinger theorem, although many other people proved it around the same time. And the theorem is simply that this statement, which equates the volume inside the Fermi surface to the density of electrons, is also present when you account for electron-electron interactions. There's simply no change to it, holds to all orders in the electron-electron interactions. So in principle, it could also hold when the electron interactions become very large. But the key step here is perturbation theory. It's a perturbative statement, and sometimes it may not hold because you enter some non-perturbative state. And that essentially will be the focus of my talk. When and how can you enter these non-perturbative states where this doesn't hold? But on the whole, it holds so well that people have refused to believe it could possibly fail because it's just thoroughly confirmed in thousands of experiments for sure that this is correct. In any metal you pick up, any metal you read about in the textbooks, this is definitely holds. Okay. Now I won't give you the complete proof of this theorem. That's a bit technical. But we are, even though it was discovered in the 60s, I think we are continue to appreciate its depth and find new ways of interpreting this theorem. And one very important fact about it is very much closely connected to symmetry. So an electronic system has a global symmetry where you change the phase of every electron operator by a factor e to the I lambda, which is independent of space and time. That global symmetry by another theorem leads to electron number conservation. And the Luttinger theorem is also very intimately connected to the symmetry and the fate of the symmetry in any phase of matter. If the symmetry remains unbroken, so the basic statement is the symmetry remains unbroken, i.e. you're not in a superconductor where the symmetry is broken, there is a Luttinger theorem. And in fact, it has nothing even to do with the existence of fermions. It could also apply for bosons if you could find a state of boson that in which this symmetry was unbroken. And another way of understanding it, which is still undergoing evolution, which this is somewhat technical comments. I apologize for that for those who care about such things. Associated with the global symmetry, there's an anomaly somewhat analogous to a 't Hooft anomaly in particle physics, where you take a global symmetry and try to gauge it. In this case, you gauge it in time with just a linear time dependence, e to the I omega t. And this kind of gauging will just change the Green's function by shifting the frequency by capital omega. And this Luttinger theorem, it's independent on interactions, follows from the fact that there's something called the Luttinger-Ward functional, from which you can generate all physical properties. And this functional doesn't care about this frequency shift. So that's one way of seeing that this is connected to an anomaly. And the role of symmetry is really important. Okay, so now, of course, let me return to the question, what happens if, this is a perturbative statement, but what if the repulsive interaction between the electrons becomes essentially infinite on all or some sides of your crystal? And I'm just going to always ignore the possibility of translational symmetry breaking because that's a lot of complication. It can happen, but I'm more interested in the case, what could happen without breaking translational symmetry? Okay, so that's the basic question. What if the interaction is so strong that this perturbation theory somehow fails? So one place where interactions are extremely strong is also called Kondo lattice systems. So here's an example: cerium, cobalt, indium 5. So of course here the electrons, it's a very complicated crystal with the electrons forming complicated bands. But what is true that there's a one band of electrons, which is on the cerium in this case. It's in the cerium f orbital, which the electron basically doesn't move. It's fully frozen on a given site. And on that site, all you have to worry about is the spin of the electron. And the reason it's frozen is because on the f orbital, the Coulomb repulsion is so strong that if an extra electron came here, that would cost essentially an infinite amount of energy. So we just don't worry about that process. So, but once you freeze the electron on this site, then you can think of this as some kind of abstract qubit. It's just some two-state system. It need not even be an electron. If you replace the electron by a qubit made up of your favorite qubit, it could be a nucleus, it could be anything. As long as it had the same coupling to the environment on the spin degree of freedom, you couldn't tell. Okay. So from that point of view, it seems like this electron is not moving at all. It's just a spin. Then it raises the question of, is this or is this not part of the Fermi surface volume? Before I get to that, so I'm not going to be drawing this complicated structure. The pictures I'm going to show you are this cartoon picture here. And they form what's called a Kondo lattice. So there's some set of electrons that are free to move, which I'll call the C electrons. And they're whizzing through the lattice. They're completely mobile, just like they are in ordinary metals. And there's another set of electrons, which I'm going to call the F electrons, which are essentially stationary, and only their spin is free to rotate. And in between the stationary electrons and the mobile electrons, you have what's called the famous Kondo coupling. So the Kondo coupling is essentially a spin exchange interaction between the localized electrons S and the mobile electron that happens to be on the same site. So this I labels the site. So if I'm on this site, then this F electron interacts with the spin of whatever electrons happens to be on this site. There could be no electron there. There could be 2 electrons there. There could be 0 electrons there. You just add up the spin of whatever is there, and that's going to interact with this. Okay, so that's the type of model that we want to study and ask the basic question: if this is a metal, what is the size of the Fermi surface? So from the perturbative point of view, if I take the perturbation point of view, these are electrons. These are F electrons even in real life. And I can imagine trying to describe this crystal starting from no interactions. So and I gradually turn up the interactions on these F sites, and as I'm doing that computation, to every order in the computation of the interaction on these sites, I would conclude that the size of the Fermi surface can't change because it's an invariant that controls the status of the metallic state. So from that argument, you would conclude that even these qubits should be part of the Fermi surface volume. So this is what we call the large Fermi surface, typically referred to as size 1 plus p. P is the density of the electrons here, and 1 is the density of the F electrons because there's 1 electron per site. So the size of the large Fermi surface is 1 plus p. So that's one point of view, just a perturbative point of view. But the other point of view, which also is a naive point of view in some ways, well, these are not electrons. These are just qubits. They're not moving. Why should they be part of a Fermi surface, which is really about moving electrons that can carry current? These objects don't carry any electrical current, so the Fermi surface should be small and have size p rather than 1 plus p. So that's really the basic basic issue that arises in study of Kondo lattices. as I said, if you did perturbation theory, there's a clear answer. The Luttinger theorem, the Fermi surface to be large. So now the history of the field is, of course, this question came up already in the 80s, and when the so-called heavy fermion compounds were discovered. And there was a lot of exciting theory that I'll briefly mention later, including by our chair. The conclusion was from those theories, and also which agreed beautifully with experiments, that the answer is the first one. This is the correct answer, and the Fermi surface is large. You should count the spins. Perturbation theory is perfectly fine, and the Luttinger theorem holds. To the extent that people started calling it a theorem because it seemed to be just always true. And that situation is, of course, now changed. Not of course. I will show you some very recent data that you could also get the other answer. But before I get to that, let me also now talk about a somewhat different system, also of great interest, in which you have the same issue, but in a not quite the same type of model. So what happens if the repulsive interactions become very strong on all or some sites? And now I'm going to consider the case of the cuprates. And instead of the Kondo model, we're going to talk about the TJ model. So here, again, this is an actual crystal structure, which you can just approximate by a single layer of copper and oxygen. And I'm going to approximate even further by just focusing on the copper atoms. And in the interesting regime, there's essentially one active orbital on each copper site. So we just simplify it to 1 electron per copper site. Now, if the density of electrons is such that there's exactly 1 electron per copper site, then in fact, the Coulomb repulsion on these sites is so large that the electrons don't move. You get an insulator. And furthermore, because of residual exchange interaction between them of strength J, they form this perfect antiferromagnet where one sublattice is down and the other sublattice is up. But this is, not the exact ground state in the insulator. There are a few quantum fluctuations due to this coupling J, because it also has a transverse SX coupling. And so there can be fluctuations of spins like that, and then back again. All right, so that's the end, but those are small corrections to the basic state that's shown here. But now you add in a few density of holes by changing things outside the layer. And now these holes, you can see, can move around with amplitude T. That's the hopping T, and that's why it's called the TJ model. So this can hop here with amplitude T and there. And then they can exchange back, but this is not allowed. This is because there's a strong repulsion on each side. So that's our infinite interaction. This is basically not allowed, and so that process doesn't happen. But still, charge can move around with amplitude T, and the spins can exchange, and so on. Okay, so what you've got now is the mobile holes of density P, that's what I'll call P, the density of these holes moving through the lattice. Okay. All right, so now the question again becomes, so as these holes move around, of course, eventually it becomes a superconductor, but let's imagine our temperature is higher and we want to understand the metallic state. So you're going to form a metal, and once you get a metal, the first question always is, what is the size of a Fermi surface? So what would Luttinger theorem say? Well, the Luttinger theorem, because of its success in the Kondo lattice, would say it should have a large size because things are moving. These are electrons that are moving around. The number of electrons is 1 minus P. And so you should have a large Fermi surface of size 1 minus P, which is actually equivalent to 1 plus P holes, because the holes in the free electron picture are measured with respect to the fill band. And you can put 2 electrons on each side. So you should get a Fermi surface of size 1 plus P of this type of holes, but again, rather similar to the Kondo lattice. The large Fermi surface has size 1 plus P. And that's what a perturbative argument would tell you if you did perturbation theory from the point where this process was allowed. and then slowly removed it, then you would conclude that the Fermi surface should be large. Okay, but on the other hand, you say that sounds really unreasonable. What's moving around are the holes. These spins are not moving at all. They're just sitting there. They're just flipping their spin. What's actually moving are the holes. So the density of holes that are moving around is P. I can just see that with my eyes. And so you would say the Fermi surface should be small. Okay, so here there are, again, a reasonable argument of either a small or a large Fermi surface. And that's the basic issue that I want to address here. So to give away the punchline of my talk is that in both cases, both things do happen. Theoretically, there are theoretical models where you can get either answer. And that there's increasing evidence from experiments of the same. Now there are experiments showing both options. And that's really, recent developments that I want to discuss. Okay, so that's basically the general introduction on the basic question and the basic systems I'm interested in. I'll pause here for a minute, Hye-young, in case there's some question on the chat.
Yes, so we have a question, and
I can't hear you.
Oh, you cannot hear me? Do you hear me?
Sorry, I can't hear you, Hye-young.
Okay. I can hear her, Subir, so I don't know if there is some...
Can you all hear me? Maybe you can just nod.
Yeah, we can hear you, but I don't, and I can hear Hye-young as well, so I don't know if there is a...
Hye-young, can you hear me?
Yeah, I hear you.
Okay, you can hear me. I can't hear you.
Oh, okay.
All right, well, I'll continue then.
Yeah, so Subir, can you hear what I'm saying?
The rest
or
can hear me. All right, so now this is the outline of what I'm going to talk about. So I'm going to go back first to the Kondo lattice model and discuss cerium, cobalt, indium-5 a bit more. And then I'll just come to the TJ model where, understanding this violation of Luttinger theorem has been a big issue for many, many years. There have been many attempts made to understand it. And I'll give you our latest attempts, which we think go a bit farther than previous attempts. All right, but let's first consider a Kondo lattice where the issue is actually a bit simpler. So the basic effect that underlies all the interesting things happening here is something called the Kondo model. So the Kondo model was proposed in the 60s by Jun Kondo from Japan, and this is my cartoon picture of it. You've got a conduction band of electrons and only one spin. So this is some kind of impurity. So we think of this as a quantum impurity model, F electron with some exchange interaction with the conduction electrons. And what Kondo showed, and was understood more deeply by many, many subsequent works, was that at low temperatures, this coupling of this spin to the conduction electron becomes stronger and stronger and stronger. It scales essentially to infinity, this exchange coupling. And in fact, there was a lot of mileage made by an analogy. In fact, the RG was developed partly to understand the growth of the Kondo coupling with scale. And in fact, the RG equations for the growth of the Kondo coupling are quite, in fact, identical to the equations for confinement in quantum chromodynamics, where it's the gauge coupling that becomes stronger and stronger as you go to longer distances, where it leads to confinement. And here, the analog of confinement is that this F electron basically dissolves, if you wish, becomes part of the Fermi sea in a way that there is no magnetic moment left on this site. It just forms a singlet with the conduction electron. And that renormalized state with no free spin left here, then this is the correct way to think about the ground state at low energies. All right, so that's just a quick summary of really 20 years of work of a deep understanding of the Kondo effect. But let's just jump ahead to the Kondo lattice then. We have a whole lattice of spins, and they each are coupled to the conduction electron. So if I just extend the theory of the Kondo model to the Kondo lattice, and say, well, all of these spins are going to dissolve into the Fermi sea. And this is something that many people worked on in the 80s, including, I think, somewhat late 80s by He-Yang Ki. You get a state where all those spins effectively disappear, and via their coupling to the conduction electrons, you get a large Fermi sea. So this is what I mean more precisely by dissolve. That the conduction electrons the spins get coupled so strongly to the conduction electron that they are effectively mobile. They just become part of the mobile quasi-particles. And this effect leads to an expansion, quite remarkably, of the size of the Fermi surface. Okay, and so the size is 1 plus P. And indeed, in all of the heavy fermion compounds, this is seen extremely well. So this is one of the great triumphs of theory of a highly non-trivial phenomenon of these spins actually becoming part of the Fermi sea. One simple way to understand it is by just writing on a trial wave function. And the trial wave function goes like this. It says, imagine that the F electrons actually had no interactions, just treat them as free. So if the F electrons are free to move around, then the C electrons are also free to move around. You just form a free fermion state of the C's and the F's, which is what we call a Slater determinant. So that gives you a trial wave function. Now, this is a terrible wave function because it's got components on it where you have 2 F electrons on this side, and that costs a huge amount of energy. So the trick was invented, sometimes called the Gutzwiller projection, where you just drop that part of the wave function. This wave function, when you write it in the site basis, has lots and lots of terms and factorial terms, and you just drop out the terms which cost a lot of energy and just keep the rest. And this type of projected wave function, then you can use as a trial wave function for the Kondo lattice. So the essence then is, what is this projection? What does this mean? Well, it was found numerically, and that it doesn't do much damage. In particular, it doesn't change the size of the Fermi surface. And so that's one way to understand this. But today there's, I think, a more general and powerful way to understand what's going on, and that's really have to use the language of gauge theories. So what's I think a better way to understand this today anyway? This rather remarkable state with a large Fermi surface. So you take these F electrons that were here and write your spin operator in terms of these F electrons. But you put in a constraint that the number of F electrons is always 1. So there's a local constraint that F dagger F equals 1. And under that constraint, you can see that the spin operator is completely invariant under this symmetry transformation. F goes to e to the I theta times F. And this theta can be a function can be different on different sites. And the reason is there's no F dagger F term between 2 sites. So you don't ever have to worry about that. And so you can choose a theta, have one value on site 1, another value in the next site, and each of their spins will remain invariant under this transformation. So when you have a local symmetry like this, we call that a gauge symmetry. And so in fact, by introducing the F electrons and requiring them to have just one F electron per site, I have introduced a gauge symmetry. So what is the physics of the Kondo effect then? Well, as a gauge theorist, you say, well, if you have a gauge symmetry, the question you now ask is what phase is the gauge theory in? Is it confined? Is it in some kind of deconfined phase, or is the gauge theory Higgsed? So here the answer turns out to be the Kondo effect is really a statement that this gauge symmetry has been Higgsed. And there's a Higgs condensate, which is the overlap between the mobile electron C and the F electrons. So if I look at this composite operator, which is two fermions, so think of it as a boson, which could condense. This is what we call the hybridization. This object carries a gate charge because F carries the gate charge, but C does not. The mobile electrons are gauge invariant. They're not restricted to have one electron per site, the C electron, but the F are. So this carries a gate charge. So this is like a boson operator with the U1 gate charge. And when it acquires a non-zero expectation value, that means effectively that the F electron I can annihilate an F electron. When there's a non-zero Higgs condensate, I can take an F and move it to the C from here to there. And that allows the F electrons to move. In fact, this is very analogous to the usual Higgs phenomenon in the theory of weak interactions, where the Higgs field gives the fermions a mass, and that's like a psi-bar site condensate, and this is very much the same thing. So that's a fancy way, if you wish, of talking about, but really a very powerful way of talking what's going on in this rather remarkable state, which is actually, again, seen in many, many, many times and thoroughly experimentally confirmed that this is what happens, that because of this Higgs condensate, you get a large Fermi surface. So here's some recent data by the group of Jim and Lattice at Berkeley. The way you measure the size of the Fermi surface is by measuring quantum oscillations, something Stephen Julian does a lot of here in Toronto, where some physical property, in this case it's the torque magnetometer, I think, varies as a function of the field, and from the oscillations of this field, of this torque, which you take a Fourier transform, you get various peaks. And then from the position of these peaks and how they depend on angle, you can read off the Fermi surface. So in this case, the Fermi surface is not a simple sphere that I showed you earlier. It's extremely complicated, but all of these details can be beautifully understood by experiments of this type. And when you do this in a certain density regime of cerium, cobalt, indium 5, indeed you find a large Fermi surface where this Higgs phenomenon, this Higgs mechanism has happened. So that opens up then my discussion of how could you get a small Fermi surface? Well, it must be that this gauge field must be deconfined. I mean, that's really the simple answer. The Luttinger volume can be violated when you don't have the Higgs condensate. Now, the theory of weak interactions, we always have the weak Higgs condensate. Maybe in the early universe it wasn't there. But in condensed matter, we have other knobs to tune, and we can, we hope, in the right experiment, get rid of the Higgs condensate. And if that happened, then there'd be an emergent gauge field, and these F objects would actually become mobile. They'd be carrying spin but not charge. There'll be fractionalized excitations. And some way of saying, at least if this was an insulator, you'll say this as topological order. So that view is not quite applicable here because this is a gapless system. Okay, so when the gauge field was Higgs, the gauge charge effectively becomes identical to the electron number because there's a non-zero overlap. The gauge symmetry is just completely broken. And then there's only one Luttinger theorem associated with the global conservation law of electrons, and that's what gives you a large Fermi surface. And on the other hand, when the gauge field is deconfined, then really you have to consider the gauge charge and the global charge as separate charges. Each of them has their own Luttinger anomalies that you have to worry about. So for the right spin liquid on the F sites, that Luttinger anomaly will be satisfied. And so the global anomaly only has to work with the conduction electrons. And so you can get a small Luttinger volumes. And these connections between, we didn't quite call it anomaly in those days, but effectively that's what it is. And the Luttinger theorem were discussed in these papers, including very clear paper by Arun in 2004. Okay, so now let's apply this to the Kondo lattice. So this is just a description of a large Fermi surface where you have a Higgs condensate and you get the heavy Fermi liquid state, which is seen everywhere. So now what would it take for the Higgs condensate to disappear? So let's remove the Higgs condensate. And so now you have an unbroken gauge symmetry. And what's happened in terms of the wave function? Well, I've just shown you a picture here. What's happened is the F electrons now form singlets with each other. They form a spin liquid. So you have two components to your state, roughly speaking. You have the mobile electrons that form a small Fermi surface. And these F electrons, have a resonating valence bond type state, which has fractionalized spin excitations and an emergent gauge symmetry. Okay, so that, and how can I write down the wave function? Well, it's a very similar wave function to what I wrote down for the FL state, but now I take two Slater determinants. I don't mix them up. There's no hybridization. They can't convert to each other because there is no Higgs condensate. So I have a Slater determinant of F and so the determinant of C, and just do the projection only on this part, and this first part will give you a spin liquid and the other part will give you the mobile electron. So this is, in some sense, the very naive thing you might have first guessed at if you didn't know anything about everything that people had worked on in the last 20 years in the theory of metals. You would just say, oh, this is what should happen. And indeed, that's what happened. The reason why it's so subtle is because getting the spin liquid state without any broken symmetry requires the development of topological order. And that's, of course, been something that's we've started to understand since the early 90s. Okay, so then here's a summary of the basic picture then of possible phases of a Kondo lattice. You have the deconfined phase where there is no Higgs condensate and that has a small Fermi surface. And you have the Higgs phase where you have a large Fermi surface. And in between, there is a phase transition where the Higgs boson goes from being uncondensed to condensed. And then you can write down a theory for it. It's not a relativistic theory. It's got a Fermi surface and all kinds of complicated things. And we continue to work on these type of theories. But the underlying phenomenon in terms of gauge and global symmetries is not that different for what people in particle physics have been talking about for a while. So let me just mention again this paper of James Analytis, what they also showed in the same paper, as they changed the density of electrons very, very carefully, that there was a change in the frequencies that they saw. And you went from this set of Fermi surfaces to this set of Fermi surfaces. And then you can understand these Fermi surfaces just by ignoring the F electrons. They assume they're localized and only have the conduction electrons. And at the same point that the frequencies change, they also saw a change in the Hall effect, which is another way of measuring the density of the Fermi surface. So then, you have two phases in principle here, the FL star phase with a small Fermi surface and the heavy Fermi liquid phase with a large Fermi surface. Okay, so I have about, 10, 20, 15 minutes left. Is that correct, Heyang?
Can you hear me now?
Okay, all right, I'm going to assume that's the case because I can't hear you. You can just raise your hand, you can point with your hand. Tell me with your fingers how much time I have. All right, 15, great, okay. All right, so I'll now get to the other part, the TJ model, and talk about possible Luttinger violation. So this has been a problem of intense interest, really, in many ways, since the discovery of the cuprates and high temperature superconductivity, and many attempts have been made to talk about phases of matter which don't obey the Luttinger theorem, including by me. But I'm quite excited by our latest attempt, which goes beyond previously what I will now say were unsuccessful attempts, but let's see. All right, so just to summarize, this is what I said earlier. Here we have the TJ model of holes moving around in a background of an antiferromagnet. And there are arguments here that seem reasonably plausible arguments that you could have a large Fermi surface of size 1 plus p or a small Fermi surface of size p, and which is the correct one. So here, in fact, we have to look to experiments because theorists, gave every possible answer you could imagine. And experiments have slowly evolved where I think now the situation is becoming fairly clear. Some very beautiful, remarkable experiments. And so I'll show some of the recent and not so recent experiments. So here is a photo emission experiment, which for now we can just view as a direct way of finding where the Fermi surface is. And when you do this at large density P, that is, when you have a fairly large number of holes above around 20%, then what you do see very clearly, and essentially every experiment, including photo emission, you see that the Luttinger volume holds. It's 1 plus P. This is the large Fermi surface. There's 1 plus P hole and 1 minus P electrons. And these are the occupied states. And in fact, this is pretty close to the Fermi surface you would compute if you just didn't worry about this thing too much and just did, density functional theory, where you just treated the interactions in a kind of a mean field way. You get the right answer. Okay, but as you decrease the value of P to below around, 0.15, depending on the particular material, things change. And at low doping, you get this structure that's sometimes called a Fermi arc. This is another cuprate at 0.1, 10% doping of holes. Sorry, that should be P. It's the same thing at P, X. So you see something rather mysterious. It's sometimes called the Fermi arc spectrum. It's hard to tell where is the Fermi surface. The Fermi surface is a closed curve. This doesn't look like a closed curve. It's just an arc. I think most people believe, and I certainly also believe, that in fact this arc is part of a small Fermi surface like that, and you just can't see the backside because it's not very intense. All right, so, but anyway, so that's been a situation for quite a while. I'll just show you one of the more recent experiments from last year by the group of Brad Ramshaw and Louis Taillefer. So this is not a cousin of the experiments on quantum oscillations. Here you're not detecting oscillations as such, but because these samples are much dirtier, you can't see the oscillation. We'd love to see oscillations at these fields in this system. But it's angle-dependent magnetoresistance. Where they look at the magnetoresistance as a function of angle, and then along with some theory, try to deduce the shape and size of the Fermi surface. So if you do this at large P, this is the kind of data, and this is the modeling, you get an extremely convincing answer based on the large Fermi surface. Okay, just again, consistent with photo emission and everything else. So there's really no doubt as to what's going on here. But at low doping, well, the situation is complicated. They do see some oscillation, angle-dependent magnetoresistance oscillations here as a function of angle, and they try to model it with various possible Fermi surfaces. And the one that works best is this one, where you had what I just surmised in the previous picture, that there is indeed a pocket. Now, the point is that a pocket would be much more visible in quantum oscillations of these types than in the photo emission, because the photo emission, you're really taking the electron out of the sample. So the probability of that happening depends on the overlap between a free electron and the normalized electron inside the sample. And that overlap could be quite small. And so you have to worry, that could account for the fact why you don't see the backside of the pocket. Whereas in this experiment, nothing's coming out of the sample. You're looking at the quasi-particles, whatever they are. And so in principle, you'll be very sensitive to the back, equally sensitive to the back and the front side. Anyway, so that's the experimental situation right now. And what I want to do is present a theory for such a state in the remaining 10 minutes or so, or maybe less. So here's a quick summary then of the theory I'm going to present, that at high doping, you have the regular Fermi liquid with the large Fermi surface, the volume 1 plus P. And at low doping, we have an analog of this FL star state that I told you about, where there was violation of the Luttinger volume, and you have a Fermi surface of size P rather than 1 plus P. But a major problem here is, what do you mean by small Fermi surface in the TJ model? In the Kondo lattice, it was pretty clear. You take the F electrons and stop them from moving. And then you get a small Fermi surface. But here, there is no distinction between F and C electrons. Everything's the same. So how do you freeze some of the electrons and not the others and get a small Fermi surface? That's really the heart of the difficulty in this entire, in my view, of the entire high TC problem, because we don't know of a good way to do that, and there's no shortage of attempts. So I'll give you our latest ideas and my talk. But let me first draw a few pictures of how you could argue that you get a small Fermi surface. Okay, you start with this antiferromagnet with a few holes, and let's imagine that because of spin, you lose your magnetism very quickly once you put a few holes, and so that, let's say that this electrons form spin singlets like this, and these spin singlets, so each one of these ellipses is this spin singlet state, the EPR state that I've mentioned in my talk yesterday, and then these singlets resonate with each other in what's called a resonating valence bond state, and these resonate around. And then you can also have these holes, which I'm now going to call holons, move around. The reason I'm calling them holons rather than holes is because they don't carry any spins. They're not like the opposite of an electron. Opposite of an electron is a charge plus E and a spin a half particle. This is a charge plus E and a zero spin particle. So that's the holon. So this holon can move around. And if this holon is a fermion, which was one of the states you considered in this paper with Young Beck, then you get what you'd call a holon metal. And so there'd be a Fermi surface of size P of these holons. But that's not what's seen in the experiments. What you've seen is a Fermi surface of holes, not holons. So how can you get a Fermi surface of holes? Well, you need some spin. So imagine for some reason, some of the spins break apart, don't form a singlet. And now the spin a half can also move, but that's costing you some energy. But maybe there's an attraction between a holon and this spin-on, this free spin a half that's moving around, so that they like to bind, and they bind into an actual electron. So this green ellipse is now a linear combination of a spin and an empty site. So now this is like a hole because it's got charge plus E and a spin a half. It's a bound state of a spin on and a holon. And so this bound state, which way am I going? Can now move around. And there, I finally have a picture of what's seen in the experiments. I have a small density of charge plus E spin a half objects moving in a background of singlets. Okay. So that's really the best I can get. And so there's been, enormous number of attempts to describe this kind of state. And in the end, they're not fully satisfactory because they always have to appeal to some things that are completely under control, not under control, to bind. First of all, you got to take the electron and then break it apart into holons and spin-ons. And then you got to take the holon and spin-ons and then bind them back again. And somewhere along the way, you lose control. You don't have a real theory. Okay. So to address all of these difficulties, I've written innumerable papers over the years. So now I can tell you, you don't really need to read any of them. You should read the latest one, which has a new idea. Let's see. Pretty soon I may discard this too, but I'm pretty excited. I think we have now made some progress in this very difficult question. So, and the basic idea is actually, I should say, really due to Yahui Zhang, or the postdoc at Harvard. So the idea is the following. So here we have a one-band model of electrons moving around. That's all we have in reality. But just for the fun of it, imagine that we had some hidden layer, some additional qubits of spins, not just one layer, because that would lead to issues with the Luttinger theorem and all kinds of anomalies. You want two layers. Okay, so these are qubits, which are called psi and psi tilde. And you can view them as just some and additional degrees of freedom I'm introducing just to make my life simple, to allow entanglement of a non-trivial kind. I mean, it's no different from the good solar projection method, where also you said, well, let's allow the electrons to have doubly occupied for a while. And then I write down a wave function, and then I get rid of the doubly occupied sites. I'm doing the same thing here. Let's just allow some additional states locally, and then we'll get rid of them. So if you had this hidden layer of two layers of qubits with a large J perp between them, then the simplest thing is that these will just form a singlet. So this is this kind of trivial singlet state you couldn't form if you just had one layer. This is just rung singlets, as we call it, and they just have a huge gap. They're basically as if they're not there. And then these electrons will just form a large Fermi surface, and that's how you get the large Fermi surface of size 1 plus p. Okay, so far I haven't done anything too shocking. I've just introduced some extra degrees of freedom and then gapped them out. All right. However, okay, now when I introduced these spins, I did introduce some gauge symmetries. And the fact that they form these tightly bound singlets means that the gauge symmetries is fully confined. You don't have to worry about them. There's only protons and no quarks. Okay, but however, we want to now break some of the gauge symmetries, of course. We want to introduce a Higgs field. So what we're going to do is introduce a Higgs field between the physical layer and the first hidden layer. So the first two layers will be formed this large Fermi surface state, very similar to the Kondo lattice, which is seen in experiments for the Kondo lattice. But here we're going to form a combination of the first two layers. Now, what's the density? What's the size of the large Fermi surface here? Well, I have density P here and 1 here. Sorry, I have density 1 plus P of holes of electrons and P and 1 here. So the density is 2 plus P of holes, which is the same as P. So in fact, in this model, what I call large is actually small. So this is a small Fermi surface of size P on this layer. And I have a spin liquid on the second layer, so with fractionalized excitations. So this is my wave function. I make a slated determinant of the first two layers, slated determinant of the last layer, and do a projection to spin singlets so that I get back to the physical space across the rungs of this layer. Okay, sorry. And yeah, this forms a spin liquid. Okay. So the gauge theory language is that I had a bunch of gauge symmetries here. The first layer is Higgs to form a small Fermi surface with the physical layer, and the second one forms a spin liquid, and fractionalization is present. And this is then our trial wave function for the FL star. So you can work with a wave function like this and compute spectral functions, and they do actually pretty well simulate what's seen in the experiments. And then, okay, I'm ending here. You can, go to town with this gauge theory to really treat all of this in some systematic way that was not possible before. So as I said, you have, it turned out you have two gauge fields here corresponding to the fact you have two layers, roughly speaking. They turn out to be SU2 cross U1. Amazingly, the same gauge theory that you have in the theory of the weak interaction. Although the quantum numbers of the Higgs field are different here. There's a Higgs boson, which is again the hybridization, but it's not just a U1 Higgs boson, it has quantum numbers of both of these gauge fields. And in one phase, in the Higgs phase, you have a small Fermi surface here. In the confining phase, you have a large Fermi surface. Anyway, okay. So that, I admit, was technical, but let me just summarize. Hopefully most of you with me, except maybe the last few transparencies. So basically the main theme of my talk has been what we sometimes call FL star, that there is a new phase of matter, which is metallic, which does not obey the usual Luttinger theorem. And there's a requirement that at any such state, there have to be some emergent gauge fields to account for the failure of the Luttinger theorem. That is anomaly that you thought was realized by a large Fermi surface is actually realized in a different way. And for that, you do need an emergent gauge field. There's some evidence in cerium copper 5 that such a phase is indeed present. And there was also an earlier work by Zhao et al. In cerium palladium aluminum. This is Frank Steglich's group, which also had evidence for such a phase. The hard question for the future is really, can you get such a phase for the TJ model? Because it's so far, at least in abstract, consistent with many, many experiments. And to get such a phase in theory, you need some kind of democratic localization of some of the spins. And one way to do that seems to be this ancilla. That's really, in my opinion, the best way that I know of to do it so far. And this new method gives us certain predictions for the critical point, which, well, okay, one of the predictions is that there are additional Fermi surfaces of ghost fermions near the transition. And if you compare the data on the cuprates and cerium cobalt 5, you see in both cases a jump in the Hall coefficient. But in cuprates, you see a large peak in the specific heat, which seems to be totally absent in cerium cobalt 5. And this is something at least consistent with the new model that I presented. Okay, so thank you very much.